All right, this is problem number 59 from section 5.4. We are given a graph, and they say that this graph is the graph that's found in that portion of our integral. That position is found from the integral from 0 to t of f of x dx. That means, by the way, that this is essentially the velocity function, or actually velocity is a function of x right now. So what we're saying is that this integral expression is really an expression of displacement. How much has the particle moved from time 0 to time t? You agree, Megan?
Yeah.
All right. So it asks, first and foremost, what is the particle's velocity at time t equals 3? Well, what is that going to be? That's going to be, this is not only the f function, it's the velocity function. It is the value coming out of that function at that location. I say the value, the velocity is f of 3, which is equal to 0. Now, they did it slightly differently. They said, you know what? Hey, if you want to find out what the velocity of something is, you're going to have to take the derivative with respect to time of position. You have to take the derivative with respect to time of the integral from 0 to t of f of x dx. But what does the fundamental theorem of calculus part 1 tell us about that derivative? Oh, that it's f of t. So, same idea. We get the same answer here. What is the acceleration of the particle at time 3? Well, wait. We've got that the velocity is f of t. How do I find the acceleration? Take the derivative of velocity. So, let's go ahead and do that. Let's take the derivative of f of t. That's going to give me acceleration. And what is the derivative of f of t? F prime of t. So when they ask what is the acceleration at time 3, it really translates to what is f prime at 3? Or what is the slope of this equation at that time? 2?
It doesn't matter.
It's asking if it's positive or negative.
Oh, is it positive or negative? Oh, it's positive.
I did too much.
It's positive.
It's 2, right?
It goes, this is a rise of 6, this is a run of 6. No, the acceleration is 1. Over 1, up 1. All right. What is the particle's position at time 3? Particle's position, this is part C. The particle's position, which is s of 3. Well, according to this formula, it's going to be the equivalent of 0 to 3 of f of x dx.
Right. Yeah, it's rising 12.
Rising 12. Oh, it is rising 12. Sorry. I'm sorry to say that Meng was right. I'm sorry to have to say that Meng was right. And now that's in recording forever. All right, let's finish. Let's go back to this question. What's the position at time 3? Well, what is that integral? What does it mean to say the integral from 0 to 3 of f of t? It means we want that area, which is purposely drawn in red because it's negative. It's the quote-unquote negative area. Its position then is going to be negative. It's a triangle that has a base of 3 and a height of, no, just 6. So negative 1/2, 3 times 6, negative 9. Do we have any units here? Yeah, meters. Okay, how about part D? Where does the particle pass through the origin?
Following an
The Ruth Ellis Center exists to provide an unwavering safe space for LGBTQ youth who oftentimes have been kicked out of their homes.
We're not going to get this recording here.
Holiday bake sale will be utilized in aiding the Ruth Ellis Center. The bake sale is December 14th.
You got 5 more minutes? You sure?
The Philosophy Club meets at lunch at room 171. Tomorrow morning, coffee, hot chocolate, and pastries will be for sale before school in a stack of $1 each. The holiday bake-off is Wednesday, December 16th during lunch in the East Gym. $2 charge to be a taster. Chinese Club members, we are going to make a holiday card by learning Chinese painting this Friday, December 18th. If you are interested, please come to room 126 to sign up during lunch hour. This has been Daily Recash with today's announcements. Have a wonderful day.
They always give like.
Okay. So let's start off with the fact that we know that this particle is at 0. It's going through its value is 0. When this integral, when t is 0, because the integral from 0 to 0 is always 0. The integral from a to a is always 0. So the next question would be, when are there other times? When are there other times that that f of x d, the integral from 0 to t of f of x dx, when are there other times where it's equal to 0? Well, I see a negative area here. Here is a positive area there of the same amount. I would say that at t equals 6, we're going to the displacement is going to be 0 again. And then if we continue on, all of the area here, it just keeps on getting positive, more positive, more positive. It never goes back to 0. So I'd say that only at t equals 0 and t equals 6 do you end up having the thing going through the origin. Yeah, Jolie?
You just like for mine, I wrote an equation like for the line leading up to like the curve, and then solved that for when like y was 0.
Oh, okay.
Was that like, can you always use that instead of using it in close?
Yeah, you could do. I mean, if you know analytically, and in this case, it's what f of x for that little portion is what, -6 plus 2x, something like that. Is that what you use for the formula? Wait, I'm sorry. Let me do this properly. Is that what you use for the formula?
Yeah.
I got a laser print. Go laser. Okay. Then if that's the case, then that will work as long as you're aware of the strict domain that curve is being used for. Yeah?
Isn't the origin just 0.00?
Well, in this case it is, but what we're saying is that this particle sort of started at the 0, and then it moved back a little bit, and then it came back through the 0, and then went on. So it's moving like along the x-axis, and it sometimes comes through the origin. All right. When is the particle moving toward the origin?
At time 3.
And the answer is it's moving toward the origin during this shaded in part.
So it's 6?
Yep. During this part, it was moving away from it started at the origin and moved away until 3. And then at 3, it started moving back here. Now it's at 6, and it's back to the origin. And then from then on, it's always moving positively away. So it's only from 3 to 6 that it's moving toward the origin. All right. That's that.